Modern data science libraries allow users to deploy sophisticated machine learning models with only a few high-level commands. But when these models stall, overfit, or fail in production, knowing how to write code cannot save the project. Programming alone does not provide the logic needed to fix a broken algorithm. Machine learning is not a coding challenge, it is a mathematical optimization problem. The code we write is simply the implementation layer for that underlying logic. Beneath the simple syntax of a Python script lies a rigorous engine built on 4 mathematical pillars. These 4 pillars are linear algebra, calculus, probability, and statistics. Mastering these 4 domains is how a practitioner transitions from blindly operating models to actually architecting them. Linear algebra is the foundational language of data science. To process information at scale, a tabular dataset must be stripped of its human-readable labels and converted into a pure mathematical matrix. Attempting to calculate or predict outcomes for this data one row at a time would be computationally impossible at the scale of modern data. Matrix multiplication solves this by computing weighted sums for every single data point simultaneously. This specific operation is the mechanism powering everything from basic linear regression to the complex layers of a deep neural network. We also use these tools to find hidden structures within massive, high-dimensional datasets through dimensionality reduction. In principal component analysis, or PCA, we perform an eigenvalue decomposition of the covariance matrix. This decomposition identifies and aligns the data along the directions of its maximum variance, effectively compressing the information without losing its core structure. Linear algebra converts messy reality into a structured geometry that algorithms can digest. Once the data is structured, the model requires a mechanical process to learn from its mistakes. Learning, in this context, is the process of finding specific parameters that minimize an error function. We visualize this as a 3D loss landscape, moving a point from a high error peak to the bottom. Calculus calculates the gradient, a vector pointing up the steepest descent. By moving in the exact opposite direction, we execute gradient descent, stepping toward the lowest error. For deep neural networks, this precise optimization process must be repeated across millions of parameters across multiple hidden layers. The chain rule from calculus is what makes training these deep architectures possible. Using backpropagation, the chain rule allows us to isolate the exact contribution of each individual weight to the overall system error. Calculus transforms machine learning from trial and error into a mathematically directed search for the optimal solution. While calculus provides the optimization path, real-world data is almost never as clean as a smooth loss landscape. Probability provides the framework needed to interpret a model's numerical outputs in an uncertain world. Bayes' theorem is the formal rule for updating our beliefs as we encounter new evidence. Consider a rare disease affecting 0.1% of people and a diagnostic model with 95% accuracy. The 5% false positive rate incorrectly captures 500 healthy people for every 9 true positives. A positive result still means actual infection probability is remarkably low. This shows why raw model accuracy is a dangerous metric if the underlying probability distribution is ignored. Probability acts as an analytical check, preventing beta scientists from making catastrophic business decisions based on a misunderstanding of algorithms. Statistics provides the tools to make rigorous claims from these observations. It identifies the central tension in every model, the bias-variance trade-off. High bias, or underfitting, occurs when a model is too simple to capture the patterns in the data. High variance, or overfitting, occurs when a model memorizes the training noise instead of the actual signal. While these complex models perform well during training, they fail immediately when exposed to real, unseen data. The goal of model selection is to find the exact mathematical sweet spot between these two extremes. Statistics serves as the final reality check, providing the proof that a model will generalize to the future. These 4 disciplines form a single continuous engine. Linear algebra structures the input into workable geometry. Calculus takes that structure and optimizes it through gradient descent. Probability interprets the uncertainty of the resulting predictions, and statistics provides the rigorous framework to prove the model's validity. Programming languages and frameworks will change and become obsolete. These foundational equations are permanent. Mastering this mathematical engine is the difference between simply operating models and architecting the future of AI.